Welcome to this exploration of the paper that launched quantum computing as a field. In 1985, David Deutsch, a physicist at Oxford University, published Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer. This paper introduced the concept of a universal quantum computer and demonstrated that quantum mechanics could provide computational advantages over classical machines. Let's understand how one paper created an entirely new field of computer science. To appreciate Deutsch's contribution, we must first understand what he was building upon. In 1936, Alan Turing invented the theoretical model we now call the Turing machine, an abstract device that could perform any computation. Shortly after, Alonzo Church developed an equivalent model using mathematical logic. Together, their work formed the Church-Turing thesis. Any function that can be computed by any reasonable mechanical process can be computed by a Turing machine. This thesis defined the limits of computation for half a century. But by the early 1980s, physicists were beginning to question whether classical computers could truly simulate nature. In 1981, Richard Feynman delivered a keynote lecture at MIT titled "Simulating Physics with Computers." His question was deceptively simple. Can a classical computer efficiently simulate quantum mechanical systems? Feynman's answer was no. He observed that simulating even a modest quantum system requires exponentially growing resources on a classical computer. A system of just 50 quantum particles would require more memory than exists in all the world's computers combined. His radical proposal: let the computer itself be built of quantum mechanical elements which obey quantum mechanical laws. Feynman imagined a quantum simulator, a controllable quantum system that could mimic other quantum systems. He argued that nature, at its fundamental level, computes quantum mechanically, and if we want to simulate nature efficiently, we need computers that work the same way. This was the spark. Feynman planted the seed. Deutsch would formalize it into a complete theory of quantum computation. Deutsch observed that the Church-Turing thesis was really making a claim about physics, about what physical systems could do, yet it wasn't stated as a physical principle. He made this implicit claim explicit, formulating what we now call the Church-Turing-Deutsch principle. Every finitely realizable physical system can be perfectly simulated by a universal model computing machine operating by finite means. But here was the problem. Classical physics uses continuous real numbers. A Turing machine can only represent computable numbers, a tiny subset. Classical physics and classical computing were fundamentally incompatible with this principle. Quantum mechanics, Deutsch realized, might be different. Deutsch's key contribution was defining a quantum Turing machine, a generalization of the classical Turing machine that operates according to quantum mechanics. In a classical Turing machine, the machine is in one definite state at each moment. In Deutsch's quantum version, the machine can exist in a superposition of many states simultaneously. The internal states of a classical machine are replaced by quantum states in a mathematical structure called Hilbert space. The transition rules become unitary transformations, the fundamental operations of quantum mechanics. This quantum computer, Deutsch showed, could simulate any physical process allowed by quantum mechanics. The Church-Turing-Deutsch principle held. Here's where things get remarkable. Deutsch introduced the concept of quantum parallelism. In a classical computer, evaluating a function on multiple inputs requires computing each one separately. But a quantum computer can prepare a superposition of all inputs and apply the function once. In some sense, the function is evaluated on all inputs simultaneously. However, and this is crucial, you cannot simply read out all the answers. Quantum mechanics only allows you to extract limited information through measurement. The art of quantum algorithm design is using interference to make the useful information accessible. Deutsch wrote, "There are circumstances under which different computations performed in different universes can be combined." To prove that quantum computers could outperform classical ones, Deutsch constructed the first quantum algorithm. The problem: given a function f that takes 1 bit and outputs 1 bit, determine whether f is constant or balanced. Classical approach: you must evaluate f and f separately. 2 queries. Deutsch's quantum approach: prepare qubits in superposition, apply f once, use interference to determine the answer. 1 query. This toy example seems trivial, but it was revolutionary. For the first time, someone had proven that a quantum computer could solve a problem with fewer operations than any classical computer. The algorithm works through phase kickback, a quantum effect where operations on one qubit affect the phase of another, allowing interference patterns to reveal global properties of the function. Deutsch is a proponent of the Everett or many worlds interpretation of quantum mechanics, and his paper connected this interpretation to quantum computing. In Deutsch's view, quantum parallelism is literally computation happening across parallel universes. When a quantum computer evaluates a function in superposition, it's computing different values in different branches of reality. Interference between these branches produces the final result. He wrote, "Quantum theory is a theory of parallel interfering universes." Deutsch even proposed that quantum computers could provide an experimental test of the many worlds interpretation, though he acknowledged this would require both working quantum computers and artificial intelligence to properly evaluate. Whether or not one accepts this interpretation, it provided Deutsch with powerful intuition for designing quantum algorithms. Deutsch's 1985 paper established several foundational ideas: the quantum Turing machine, the Church-Turing-Deutsch principle, quantum parallelism, quantum speedup, and quantum complexity theory. Building on Feynman's vision and Deutsch's formalization, an entire field emerged. 1981. Richard Feynman proposes quantum systems to simulate physics. 1985. David Deutsch defines the universal quantum computer and first quantum algorithm. 1992. Deutsch and Josse extended the algorithm to multiple bits, showing exponential speedup. 1994. Peter Shor discovered quantum algorithms for factoring, threatening modern cryptography. 1996. Love Grover found quantum search algorithms with quadratic speedup. 2019. Google claimed quantum supremacy, a quantum computer outperforming the best classical supercomputers. Today, billions of dollars flow into quantum computing research and development. It all traces back to Feynman's 1981 question and Deutsch's 1985 answer. Quantum mechanics isn't just physics, it's a new kind of computation. Quantum theory, the Church-Turing principle, and the universal quantum computer is one of those rare papers that creates an entirely new field. David Deutsch asked a simple question: if computation is physical, shouldn't our theory of computation respect the laws of physics? Classical computers don't fully align with classical physics, let alone quantum physics, but quantum computers do. By formalizing the quantum Turing machine and demonstrating the first quantum speedup, Deutsch showed that quantum mechanics offers computational possibilities beyond anything classical physics allows. We are still exploring the implications. Quantum computers promise to transform cryptography, drug discovery, materials science, and optimization. They challenge our deepest intuitions about what computers can do. When future historians trace the origins of the quantum computing revolution, they will point to Feynman's 1981 vision and Deutsch's 1985 formalization. Two physicists who saw that the universe itself computes quantum mechanically and that we could learn to harness it.